Alright, come to another planetary problem, and again, these are all largely the same. Here, in this case, we have Saturn. There's Saturn, it's got the ring. I'm not going to draw the ring too much because I don't want you to confuse it with the orbit. Here's Titan going around Saturn, and again, Titan has a force pulling it towards the center, and that is caused by gravity. And so with this information, we want to calculate the mass of Saturn. So this all comes down to, again, expressing all the forces with some variables. So we know Fg, the force pulling Titan, is equal to big G times the mass, in this case of Saturn, times the mass of Titan over the distance between them squared. Again, the m's just get subbed in depending on what the objects are. And again, so this thing is going in circular motion. So if it's going in circular motion, there must be a centripetal force acting on it. And we can express the centripetal force in terms of m. And again, m is the object that's doing the circular motion, mt, times v of that object, so vt squared over r. So this is the gravitational force pulling on Titan, and this is the centripetal force that is necessary to keep Titan in orbit. And again, since there are no other forces acting on Titan, we know that these two things are in fact equal. So we can write these terms, these expressions equal to each other. So G ms mt over r squared equals mt times vt squared over r. And again, we look at this and we say, okay, what can cancel? The mass of Titan can cancel on both sides. This r can cancel, giving me an r here. And then what's left after this? I've got G ms over r equals vt squared. Now the question is asking for the mass of Saturn, so I want to solve for ms. So if I multiply both sides by r, I get that Gms equals Vt squared times r. Now if I divide both sides by big G, I get that Ms, mass of Saturn, is Vt squared times r over big G. That's really the answer to my problem. This will work again for any planet, but you should know how to calculate this, how you should get this expression. Again, setting the gravitational equal to the centripetal force and going through and moving things around. So now, in order to get the mass of Saturn now, I just need r, which I have right here. I need g, which I know, and I need the velocity of Titan. Now, I don't exactly have that here. I have the time it takes to go around the planet. So you may remember to find the velocity of an object going in a circle, it's really just the distance over the time. So the velocity of Titan is its distance over its time. Well, what distance is it traveling? It's traveling one complete orbit. So this is a circle, so we want to find the circumference. So the circumference here, again, is 2 pi r. So the circumference around Saturn is 2 pi times the radius of that orbit, which in this case is 1.22 times 10 to the 9th meters. So I'm going to solve for that. So 2 pi times 1.22 e to the 9th. And when I do that, I get that the distance is 7.665 times 10 to the 9th meters. The time is 15.95 days, but I want that in seconds. So 15.95 days, there are 24 hours in one day. There are 60 minutes in 1 hour. And there are 60 seconds in 1 minute. So I'll calculate that. 15.95 times 24 times 60 times 60. And I get the time is 137.8080 seconds. So now the velocity of Titan, I'm just going to be dividing those numbers, 665 e to the 9th, divided by that, and I get it's 55.62 meters per second. I'm starting to run out of room here. So that's the velocity of Titan. So I'm going to plug in this velocity into this. I'm going to plug in the radius in, I'm going to plug in g. Now, I'm pretty much out of room, so I'm just going to do this in my calculator, and so we can get a final answer here, and you can do it as well. divide by 6.67 e to the negative 11, and I get the mass of Saturn is 5.66 times 10 to the 26 kilograms. And that makes sense, a very large mass. If you remember what the mass of the Earth was, it was on the order of to the 24th. Saturn is bigger than Earth, so this is a reasonable answer. If you got an answer like 5,000 or 18,000, that should ring a bell. That's not the mass of a planet. That's just way too small. But anyway, you can do this for, again, any orbital system. If you're trying to find the mass of the central object there, you can use this equation. But again, don't memorize this equation. Make sure you can derive it by analyzing these two equations here. So practice until you are comfortable doing that. All right, so until next time, I am Derek Genova. Have a delightful day.